Welcome, everyone. You know what? We're actually going to skip the usual agenda today. Yeah, let's just jump right in, because we're diving into this completely hidden physical reality that's literally right in front of us. We're exploring the chemistry of mixtures today. We'll be pulling straight from the NCERT curriculum, and of course, using the brilliant practical teaching style of Ashu sir. So get ready, because you're about to see your everyday world in a completely different light.
Okay, so just take a second and look around the room you're sitting in right now. The air you're breathing, the clothes you're wearing, even the water you might be sipping on. Is any of it actually pure? I mean, in chemistry, the word pure means something very, very specific. We always say things like pure milk or pure air, but chemically speaking, almost everything we interact with is actually a really complex mixture. Think about the air in your room, or human blood, or even a 22-karat gold ring. Actually, Ashu sir loves to point to his own wedding ring as a perfect example of this. These are all mixtures. And by definition, a mixture has two or more components mixed together, but, and this is the absolute key here, they are not chemically combined. Plus, they don't even have a fixed ratio. Like, the air in your room might actually have slightly less oxygen if the windows are shut, compared to, say, a park outside. It's still air, it's still a mixture, but the recipe, it's not strictly fixed.
So the crucial point is, how do we divide this massive world of mixtures? Well, we split them into two distinct camps. And here's a quick memory trick for you. Just look at the prefixes. On one side, we have homogeneous mixtures. Homo means same, so these have a totally uniform composition throughout. If you dissolve salt perfectly in water, the first sip and the last sip are going to taste exactly the same. It forms a perfectly clear solution. Now, on the other side, we've got heterogeneous mixtures. Hetero means different. These are non-uniform. Think of oil and water. You can literally see the visible boundary between those two liquids. They just don't perfectly mix.
To really lock this in, let's walk through NCERT Activity 5.1. Picture 3 glasses of water. In the first one, we add salt. In the second, some chalk powder. And in the third, just a few drops of milk. Now, the salt water is a true homogeneous solution. The salt particles just disappear. They never settle. And if you shine a laser through it, the beam is totally invisible. The chalk water, that's a heterogeneous suspension. You can clearly see the particles. The laser hits them, and eventually that chalk is going to settle at the bottom. But the milk? Milk is sneaky. It looks uniform, it doesn't settle, but if you shine a laser through it, boom, the path of the light actually lights up. That scattering of light is called the Tyndall effect, and it proves that milk is actually a heterogeneous mixture known as a colloid. All right, let's zoom in a bit on those perfectly uniform, homogeneous mixtures, the ones we call solutions. Now, a solution has two main parts. The first is the solute. The solute is simply the component that gets dissolved. I honestly love Ashu sir's analogy for this. Think of the solute as the guest arriving at a party. They're usually there in a smaller amount, just waiting to mingle and mix into the space they're given.
Then we have the second part, the solvent. So if the solute is the guest, the solvent is the host of the party. It's the one doing the dissolving. Now listen up, because here is a very common trap students fall into, assuming the solvent is always water. Okay, yes, water is a universal solvent, absolutely, but it's not the only one. Take a medical antiseptic like tincture of iodine. The iodine is the solute, sure, but the solvent, the host, is actually alcohol. And this brilliantly illustrates something super important. Solutions are not just solids dissolving in liquids. Think about pure air. It is literally a gas dissolved in a gas. Nitrogen makes up about 78% of the air, which makes it the host, the solvent. Oxygen, sitting at around 21%, along with a few other trace gases, well, those are the guests. They're the solutes dissolving right into that nitrogen. It is a perfect homogeneous mixture, just floating invisibly all around us.
Okay, now we really need to talk about a concept that pretty much rules chemistry: concentration. You've probably seen a bottle of vinegar in your kitchen with a label that says something like 5% volume by volume. But what does that 5% actually mean? Well, concentration is just a handy way of measuring exactly how much guest is hanging out with the host. It simply tells us how much solute is present in a given amount of solution. Let's move to and see how this builds into a calculation. Finding the mass by mass percentage of a solution is actually super simple. You just take the mass of your solute divided by the mass of your total solution and then multiply by 100. Easy, right? But, and this is a huge entrance-level trap that Ashu sir always warns about, the mass of the solution is the solute plus the solvent. Let me say that again. If you put 10 grams of salt into 90 grams of water, your total solution mass isn't 90, it's 100.
Now, you might be wondering, Why do we even care so much about calculating this? Well, because in the real world, concentration matters immensely. Just think about an ORS packet you'd use for dehydration, or even one of those liquid mosquito repellents you plug into the wall. If the concentration of the active solute is too low, the repellent fails, and you're getting bitten for sure. But if the concentration is too high, that chemical could actually become harmful for us to breathe in. So you see, this math isn't just for passing tests. It's literally for keeping us safe.
But, hosts can only take so many guests, right? And this brings us straight to solubility. Solubility is basically the absolute maximum concentration. It's the max amount of solute that can dissolve in a fixed amount of solvent at a specific temperature. Once you hit this limit, that's it. The solvent simply cannot accept any more solute. Any extra salt or sugar you try to add will just sink straight to the bottom of the glass.
Because of this, we get two different states for our mixtures. An unsaturated solution is like your everyday glass of lemonade. If you want it a bit sweeter, you can stir in another spoonful of sugar and it'll disappear. It still has room for more guests. But a saturated solution, that one is totally maxed out. Imagine the incredibly thick, sticky sugar syrup they use to soak jalebis or gulab jamuns. It has reached its absolute solubility limit at that temperature. You literally could not get any more sugar to dissolve in it if you tried.
Now, what's really interesting about this slide is that it brings us to a fascinating real-world mystery. There's a really famous natural hot spring in Manikaran, India. The water there is so intensely hot that people actually cook rice in it. But here is a scientific question I want you to ponder. Why is there absolutely no aquatic life, no fish at all, living in those natural hot ponds? Well, it actually has everything to do with solubility and temperature.
To solve our fish mystery, we need to look at the temperature rule. See, when you heat water up, the particles spread apart, essentially making the room bigger. This means hot water can dissolve way more solids, like sugar or salt. But for gases, it is the exact opposite. Heating the water gives gas molecules the kinetic energy they need to just bounce around and escape the liquid entirely. So hot water actually dissolves less gas. Those boiling hot springs have almost zero dissolved oxygen in them, which makes it literally impossible for fish to breathe. Oh, and fun fact, this is exactly why a warm cold drink tastes super flat. The carbon dioxide gas has all escaped.
So what exactly happens if we play this whole temperature game in reverse? Let's say you've got a piping hot, highly saturated sugar solution, completely packed with dissolved solute. If you cool that liquid down, the water particles are going to come closer together again. The room shrinks. Suddenly, the water can no longer hold all that dissolved solid. The invisible solute guests are literally forced to pack their bags and leave the solution. They emerge right back into the physical world as pure, solid crystals. This really beautiful process is what we call crystallization.
To sum it up, when you cool a saturated solution, the invisible solute is forced to become visible again as pure crystals. The really cool part is that it leaves behind all the impurities in the liquid, which gives us one of the most elegant ways to purify a solid substance. Honestly, it's just a stunning reminder of the sheer physical reality of the matter that we can actually manipulate.
We've gone all the way from the air we breathe, to the gold on our fingers, to the mathematical limits of exactly how things mix and unmix. The physical world isn't just stuff, it's a giant, dynamic chemistry lab. So I'm going to leave you with this. Take one more look around your room right now. What invisible layers of mixtures, what saturated solutions and precise concentrations are hiding in plain sight right next to you? Keep questioning, keep exploring, and we will see you in the next explainer.